Hey students, Stark here with a lesson on limits involving infinity. We're just going to focus on finding and verifying end behavior models. These three things, a person, an idea, and a nation, what do they have in common? Well, they could be conceived. They can die. People in history live on. Ideas live on. A nation lives on. So I'm sure you could think of many more ways that these things have something in common. But this concept of end behavior is kind of what brings these three things together, connected to what we're going to see in functions, is that all of these three things can start the same way. They could be born, they could be conceived in some sort of way. But they all end in a similar sort of way too, or can end in that. So what we're concerned about as we approach this concept is how do these three things, or more specifically mathematical functions, behave as they end, either as x approaches infinity or x approaches negative infinity, as time goes forward or as time goes back. So let's just get a sort of loose definition of what end behavior is. Yeah, I know you're not supposed to use the words in the concept to define it, but really it's just the process of modeling the behavior of a complicated function with a simpler one. So let's get a complicated function going. So here we go. F of x is some crazy function that when you graph it in your calculator, it's a quartic function. It's sort of parabolic in nature. So I'd recommend that you graph that in your calculator now, and g of x is quite simpler. So what we want to show is that even though these are sort of really different when we look at a small window, that they're virtually identical for extreme x values, like positive and negative infinity. Okay, so that's the extreme values. So our first step is to graph the functions. Okay, so always a great first step with any limit so that you could visualize things. And then the second step is to divide them. And then the third, I'll go right over here. Third step is to take the limit. Take limit as x goes to positive and negative infinity. Really, the main focus is the positive infinity, because when you plug in the negative, it sort of does the same thing. Okay, so what I'm going to do is get the dividing thing going on with the limit at the same time, and since you have your calculator, you can graph the function and you can see what they look like. So they look different when x is small, but practically the same when x is really big. So I'm taking the limit as x goes to infinity of this quotient. So I'm going to show you two ways. I'm going to do this like sort of blue version, and I'm going to do this green version over here. So the blue version says that I can take my algebraic properties and rewrite this as 3x to the fourth over 3x to the fourth minus 2x to the third over 3x to the fourth. Okay, so I just basically rewrote everything over 3x to the fourth. So the limit as x goes to infinity of 3x to the fourth over 3x to the fourth is simply 1. The limit of that second one is 0. The third one, 0, 0, 0. So therefore the limit as x goes to infinity is 1. And just to clarify that, I guess, is that when you take something like this 3x squared over 3x to the fourth, and you plug in infinity, you end up getting infinity squared on the bottom. So in other words, I guess I could write this here since I have some space. We end up just getting 1. But this one cancels out to 1 over x squared. Okay? And that is 1 over a really large number. So that's practically 0. 0. Okay, now the green, this is a shortcut version, okay? And what the green says is that when x is really large, then none of this stuff matters. Because 3x to the 4th, infinity to the 4th is so much larger than infinity cubed. All right? So that means we end up getting 3x to the 4th over 3x to the 4th. And when we take the limit of that, we end up with 3 infinity to the 4th over 3 infinity to the 4th. Which both of these are just 1. So here's a conclusion. We found out that the quotient of those two functions is 1. So this is our conclusion. Since the quotient is indeed 1, then g of x is an end behavior model of f of x, because they're acting the same way when x is really large. Okay, super. So that's one type of question that could come up with end behavior. Here's another one, and this is the only other one I have. Find an end behavior model for f of x equals this crazy quotient. So using what we've done so far, so taking a look at this function, we just look at the top here and we notice that when x is really large, this is the only thing that matters. In other words, if we were to find an end behavior of that numerator, we would get rid of all of this stuff. So that means our end behavior of the numerator is 2x to the 5th. And we could verify that by taking the limit of the numerator divided by 2x to the 5th, and we would see that it's 1. The end behavior of the denominator is 3x squared, because when x is really large, all that other stuff does not matter. So we end up with this result here, 2x to the 5th over 3x squared. So that works. That's an end behavior model. That works. But we just take it one step further and we simplify. And we get 2/3 x to the 3rd. And this is the answer. So to verify that, because we're kind of focused on the verify part too, that we would take this function right here and we would graph it along with the original function that we were given. You know, and that's kind of a lot of stuff to enter, but it's worth verifying. So we graph these in the same window, and you start to trace it to some large values, and you start to see how these curves end up going to the same, in the same sort of, they start to meet up and touch at very large values. Another thing that would be really interesting is if you enter this f of x as like y1 in your calculator, and then this one as y2, and then you could divide them in the calculator, and then it would show you just a constant line. And if it is indeed a constant line, if it's 1, going back to this, if the quotient is 1, then that gives you an end behavior of that function. Okay, so that's finding and verifying end behavior models. There are other types of functions that you may just end up with a constant, and that's okay. You could end up with 3/5 or 5/8, and that's just a line. That means that the end behavior, it's moving towards a constant value. The limit as x approaches infinity is some value. So thanks so much for watching.